Fundamental theorem part 2. Okay, this is very closely related to part 1. Alright, but what we want to look at today is making our upper bound here some function, okay, instead of just a number. So we want to think about if we define some function to be this integral, okay, the integral from 0 to x instead of 0 to some number of a function, okay, and we want to figure out what's going on. Okay, this is going to be very closely related to the idea that derivatives and integrals are inverse operations. Okay, so what we're eventually going to do is take derivatives of integrals. Okay, I'm jumping ahead of myself. So first, let's look at this function. Okay, we've got the integral from 0 to x of t squared dt. So let's use what we talked about yesterday, part 1, and evaluate this. Okay, so the first thing, okay, would be to find the antiderivative. Right, so what would the antiderivative of t squared dt be? 1/3 t cubed. So 1/3 t cubed, and I want to evaluate this from 0 to x. So draw my bar, put my values there. So I'm going to plug in x, and then I'll plug in 0. And so I'll have 1/3 times x cubed minus 1/3 times 0 cubed, which just gets me 1/3 x cubed. Okay, so the antiderivative of something like this, if I'm going from 0 to x, ends up just being the antiderivative of this function. Okay, all I'm doing is saying, well, I want the area under the curve from 0 to some unspecified value, and I get the antiderivative. Okay, so what we want to do then is take something like this and take the derivative.
No.
No, we're not going to leave people.
I just saw her. Okay. How did you see her?
I think they just
You know what? I can speak. I can speak. I wouldn't have to ask it.
Alright, so what we want to do then is start taking derivatives of these antiderivatives. Okay? We would think that we would always end up with the function that we started with. Okay, so what we had, right, our integral there, we said the integral from 0 to x of t squared dt. Integrals and derivatives undo each other. So if I take the derivative of an integral, I should get that function, right? And that's what we just got. If I take that function that we just found with the antiderivative, 1/3 x cubed, and I take its derivative, I get x squared. Well, that's this function, right? If I plug in my x. So derivatives and integrals undo each other. However, we aren't always going to get this function, okay? So what we want to do is take a look at 3 cases, okay, and see why we're not always going to get this function whenever I'm integrating over some interval where we have a function instead of a value. Okay, so let's examine 3 cases. Okay, first, we've got the integral from pi to x of cosine of t dt. So what we're going to do is go through that process that we just did. Find the antiderivative, plug in our 2 bounds, pi and x, and then take the derivative of that. Okay, so let's do this one together. So what's the antiderivative of cosine? Right, positive sign. So I would have sine of t, and I want to evaluate this from to x. So this would just be sine of x minus sine of pi. What's sine of pi? Sine of pi is 0. So this is just sine of x. So I get that my antiderivative, my original function, is sine of x. Well, what's the derivative of that then? Just cosine. Right? So in this case, I got exactly what we expected. Right? If I'm taking the derivative of an integral, those are inverse operations, so those would cancel each other out, and I just get cosine. Okay? So you guys go try to go through this process for the next 2. Okay? Yes. Same as if, this is 1 plus t to the 1/2. Right? So add 1 to the exponent. Take the old coefficient over the new exponent. So this would be 1 plus t to the 3/2 times 2/3. So I plug in x minus 3. So in this case, okay, again, we kind of get what we would expect, because all I did was plug x minus 3 into this function, right? And I got the square root of 1 plus x minus 3, which would be x minus 2. So we got the square root of x minus 2. The integral undoes, or the derivative undoes the integral. And we end up with just this function. Okay, plugging in this x minus 3. We okay so far? What do you mean? Like, well, it's a little bit different because we didn't get this, right? We got if we plug x minus 3 into this. So it's a little different, but not a whole lot. Case 3 is the one that's going to be more different. All right, so let's take a look at our final case here. So here I'm evaluating the integral from 4 pi to cosine of x of t squared dt. Okay, so take a second, see if you can go through this process here. Find the antiderivative, plug in the bounds, and then take the derivative of that function. Yes. Yes. So when we use chain rule here, so another way that we can write this is 1/3 times the cosine of x cubed. Right, so there's a couple of layers here. First layer, bring the 3 down. So I would just end up with 1 times cosine of x squared. Yeah, then the next layer is cosine. So the derivative of cosine is negative sine. So here, I didn't quite get what we expected. Right? Undoing the integral, okay, we would think I would just plug cosine into the function and get cosine squared. But we got cosine squared times negative sine. Okay. So whenever we're taking the derivative of an integral, okay, those are inverse operations. However, we will have to apply chain rule. Right? So what that looks like, okay, down here, under the fundamental theorem of calculus, part 2, for now, yes. Right. Whenever I am going, and this, actually, let's even make this a little more general. Okay, scribble out this 0 and put an A. Okay, that can be any constant value. It doesn't have to be 0 down there. Okay, we did examples where we had pi or 4 pi down there. This can be any number, except for, or any number, not just 0. So then if I'm taking the derivative of an integral, okay, we're going to say, well, I'm going to plug this function in here. Okay, so this is going to be f of g of x, then times the derivative inside. Okay, that's what we just kind of saw in case 3 there. Okay, so let's make up a couple more examples here. So let's say, go the integral from 3 to 4x, let's say f of x equals this, of about sine of t dt. Then f prime of x equals. Okay, so all I need to do, I don't need to go through that whole process that we just did. Okay, now we can just use this formula. Say if I'm undoing an integral, if I'm taking the derivative of an integral, well, all I need to do is take my upper bound here, plug it into my function. So I'm going to say this is sine of 4x times the derivative of this function. So what's the derivative of this function? 4, right? So times 4.
So you don't take the derivative.
Right, just the derivative of this piece. Right. So, how about the f of x is integral from 17 to e to the x of 4x or t squared dt. And what is f prime of x? What would the derivative of this integral be? Four times e to the x squared, then times the derivative of e to the x, which is e to the x. Now, using a little bit of algebra, how could I clean this up? So this, this part would be e to the 2x. Wait, say that again? Yes. Which, right. Is that, that is what you said. You said e to the x cubed. Did you say squared? So if we, like that, then we would multiply the exponents and get 3x. As long as you're not saying that it's just x cubed.
No.
E to the x cubed. So if this were a multiple choice question, I bet the answer would look like that. Okay, so you would have to understand how to get from here to here using algebra. And the calculus is just this formula. Right? Plugging in our upper bounds, and we're taking the derivative of an integral, plugging in the upper bound, and then taking the derivative of the upper bound. Okay?
My hair, I would put it back up into a ponytail or a body.
That's quite correct.
No, because everyone hates it up. I can't do
All right.
it.
How about one more example? how about
Really? I
so in case 1, both of our bounds were numbers. Right? In case 2, now we're looking at, well, what if these are functions instead of just numbers? So how about this? From 2x to 5 of 2t cubed dt. This one looks slightly different than all the examples we've done so far. Why? Right, functions on the bottom. How can I fix that? Flip it and make it negative. All right, so I can say this is the same thing as negative 5 to 2x of 2t cubed dt. Right. So then we can apply this same rule. So what would my derivative of this integral be? Times 2x cubed times 2. So how can I clean that up? Yeah, we can multiply these 2's together and get 4 times 2x cubed. How about I can do a little more? Alright, so this would be 8 times x cubed. And then I can multiply the 4 and the 8 together. Get 32x cubed. You okay with that one? Alright. Now I think we're actually gonna skip the back page. That's more looking at accumulation functions, which got a whole other lesson for that.